continue our discussion on vertical axis wind turbine. Um, what we have started talking about the basic working principle of vertical axis wind turbine, and then since these are mostly drag based, so like we looked at different kind of. I think this is the last discussion topic where we kind of stopped on the different kind of these drag coefficients and how mm, they vary, because eventually your drag coefficient data is going to contribute to your mm, drag force calculation. So that is what we talked last time. Now this you could see here the multi-stage turbine. That means you have one kind of structure or the frame, and then you have mm, four, one, two, three, four turbines which are connected in one particular structure. The whole idea one can think about here is that mm, it is kind of similar of putting horizontal axis turbine in a kind of a farm. Here, since these are size, they are small in size, the vertical axis wind turbine, and they are portable also. So they can be built like that. So similar thing, one of that helical design has the similar kind of structure. So you see these blades are of helical shape, but if you see in total the footprint or the size of the complete turbine, including the gearbox and the other components, they are not very large. So kind of a four of them could be installed in that kind of a one single foundation like this. And if they are portable, if possible, they can be also some offshore installations could be carried out. uh, one of the simple reason for that, in the offshore you have a good wind availability. So once you have good wind availability, then you can always carry out this exercise, and you can install this kind of different structure of the turbines and all these things, and then make use of that. So obviously, when you use multiple of them, mm, um, the advantage that you get out of that your overall power coefficients can be increased or multiplied by that many times of this thing. So now this is again a Darius type. So this is a Darius type vertical axis wind turbine pattern, where this one you see the kind of a carved blade. But overall principle, if you see, this is a Darius type, and this is the so this probably one can think about front view, and this is probably the side view, and you could see how these airfalls are going to. Obviously, they are having some blade pitching mechanism, so airfall could change their pitch. So this is something slight different between horizontal axis wind turbine. One can think about horizontal axis wind turbine. Your blade has the rotor blade has a fixed pitch angle at a particular section. Obviously, when you go from a, if I let's say go from uh, this is hub to tip. So at multiple section, there could be different aerofoil, but you could have a fixed pitch angle, and obviously the pitch motion can be a little bit controlled, but not completely, as the wind direction changes, or if you have too much of incoming flow change and things like that. Whereas in this particular case, in the particular situation of vertical axis wind turbine, what you could do is that you have this airfoil sitting here, Now these aerofoils could be, so now this is a structure like I have a shaft like that, and mm, this is the blade of a uh, uh, vertical axis wind turbine, which would be connected like that, and they are kind of rotating. So thing is that this blade pitch angle, this could be fixed. So that means like a horizontal axis wind turbine, this could be fixed and keep on rotating, or they can have variable pitch mechanism. So this is the advantage you have compared to horizontal axis wind turbine. The situation is such that in horizontal axis wind turbine, if you try to build something with variable pitch, actually that's going to be a big problem because the turbine blade diameter or the rotor diameter is quite high. Whereas in the vertical axis wind turbine, this variable pitch mechanism could be an easily doable choice and usually done. In fact, to mention here, yeah, the similar kind of Darius concept and all these are there available in the hydrokinetic energy also. There also you have axial, which is comparable like our horizontal axis wind turbine, and this Darius type and all these they are comparable. They are also in hydro. And hydro, this variable pitch and all these are very, very handy. And they kind of mm, help you to achieve the power output and things like that. And now the point here is that so this is the advantage that you have compared to vertical axis wind turbine. In the horizontal axis wind turbine, you can achieve this kind of things. And here you could see some installation of this kind of an carved blade installation. So these are carved blade, but it's installed in a I mean kind of a farm kind of, and this is how closer view it shows that how big that is. Now, if you try to look at in little bit more details about the component and all these things, so here is the image of that where you can see what are the some I mean those important components and that one vertical axis wind turbine may have. Okay, you see this upper half, this is lower half, this is the rotor blade, and it is carved like this. Then you have generator sitting here, you have the gearbox and everything. So this is your kind of a small basement cum foundation, then only one shaft. But this height could to be high as your horizontal axis wind turbine, but usually not that much because these are for small power generation purposes, but they are quite mobile. They can be transported easily and installed to cater to the small requirement of energy demand or supply demand, such kind. So now the question is, uh, you could see this particular. This is called the another. I mean, similar concept of a small gyro mill Jarius vertical axis wind turbine. This is in Colorado where it has been installed like that. So you capture the wind, and I mean, obviously, when you are exposed to the wind, and you get this kind of what do you call the power generation which can cater to the small so that's a nice picture of basic this Darius type vertical axis wind turbine installation for local neighborhood applications or things like that. Now here, now we come back to see how these turbines actually produces the power and So as we discussed earlier, primarily there are two concepts which are mm, used. One is the drag based. So the drag based concept, what happens is that you have these blades which are sitting on the, obviously connected with the rotating shaft, and there is a concave surface and convex surface, and when the flow comes and hitting the concave surface, then it rotates, and the convex surface comes this side. So effectively, this difference in the forces and all these, that creates the torque, and that torque is finally used to produce power. So if you see the net torque for this drag based case, it's a difference between these two turbine and their torque. Uh, so what you have, so then you find out the complete torque where your drag coefficients are there, which is CD1 is one drag coefficient, CD2 is the second drag coefficient, velocity, distance from the net force, density, blade area, and all these things. So this is quite straightforward that once you consider this. The other case is the lift based. This is a Darius type of these things. So the drag based, one can think about it's a kind of the other classification that we have already discussed earlier is the Savonius kind of things. And this is the Darius kind of things where, as you see, these are the straight blades. You can clearly see this aerofoil section here. They are connected with the main shaft with the connecting rod or supporting arm. And then the bottom, you will have the generator assembly and all these things would be there. Okay. So here you have this tangential velocity, wind velocity, resultant velocity, angle of attack, airfoil chord, blade span. And if you look at one particular airfoil here, okay, and then try to see the distribution of the forces. So you could easily see the component of the lift and drag forces, and then you have the resultant forces based on angle of attack here. So again, this is your velocity triangle, kind of similar concept that we have used in the horizontal axis wind turbine. So it's a respect to, so when the wind is coming, then in respect to a particular plane of the aerofoil. So you take one aerofoil and see how that looks like, but you are looking it from the top. So this is the cross section, so that you get this cross section things. And when you look at from the top, then wind would hit the blade in this fashion because the blade is at angle of attack. So the CL and CD force coefficients one can find out. So these are the standard way to find out that. Then the tangential and normal force, which could be taken into two component of this CL sin alpha, CD sin alpha, and all these component. And finally, the power is the T into torque into omega, and torque is the FT with the radius. So that's how you calculate the things. Now, if you compare the Newton's law of motion, so then you could easily see the linear motion to the rotational motion and the parameters. So there would be position x, here the angular position theta, because it is rotating in an angle. So with the reference frame, so you'll have that theta, velocity v, here the angular velocity omega, acceleration a, angular acceleration alpha, motion x equals to bt, here theta equals to omega t, then v naught plus at omega naught theta, and v acceleration. So they go by the similar fashion, which follows exactly the Newton law of motion. Then the linear inertia m, then moment of inertia I, F equals to ma, I alpha, mv, air angular moment I omega, work fd, tau theta, half mv square, half I omega square, power fb, tau omega. So this is what we are interested in, so that once we got the torque and we get respect to that thing. Here is another picture of vertical axis wind turbine, which is again a Darius type, and this was in how you can see the structure is made such that this is can be used to go for all maintenance purposes and things like that. And the connecting arm is taking the rotor blades away from this connecting, the foundation structure, so that it never touches or there is no possibility of getting it getting it interfered, or there could be interference, all these things. So that's how the picture of the vertical axis wind turbine that you get to see. Now, if we come a little bit more details about now straight blade vertical axis wind turbine, this is the name Darius is usually associated with the curved blade version of the Darius patent. But a lot of work over the past 3 decades have gone into development and analysis of the straight blade version of vertical axis wind turbine, which is also known that H vertical axis wind turbine, or we sometimes call it H type Darius. So because the blades are straight, not curved, but the original invention of Darius was curved blade. So obviously, one of the great research came up in 1970s regarding that. Now, Giro mill is another consequence of adopting a vertical axis wind turbine is the apparent velocity of the wind in a particular location. So if you see, this is the wind coming in and the blades which are going to expose to that, and every time you have angle of attack, the theta from the center, then you have beta. So the blade is traveling upstream, because if it is rotating like that with that angular velocity, so you have local wind velocity, you have velocity due to blade movement, you have resultant wind velocity. So essentially, it's again going to, so if you see at the every blade, there is a velocity triangle associated with it. And the reason is the simple, because you have wind coming in, the blades are rotating, so there will have this R omega component, and there would be a resultant, there is a lift force also because of the flow passing over the airfoil. So obviously, you end up getting those resultant component of the force. Now, when the blade is traveling upstream, that is azimuth angle is beta 0 to 180 degrees, so beta is varying like that. Resultant air velocity on the blade is greater than the tangential velocity of the blade, which is relative to the stationary frame of reference. Now, when the blade is traveling in this quadrant, that is the third and fourth quadrant, the resultant wind speed is generally less than the tangential velocity. So that you can see from this and this velocity triangle, whereas the other two showing slightly different. So which in turn means that the blade is continually changing or continuously changing the angle of attack, and obviously may not be optimal throughout the rotation about the axis of turbine. So how to improve the situation? So to improve the situation, there are various ways it has been tried to optimize the blade pitch angle. So which is the chord angle relative to the tangent of the path of the blade as a function of beta. There are different ways one could achieve this. One is the mechanical mechanism with levers or push rods connecting between the blades and the main rotor shaft. or aerodynamic mechanism. So one way you try to control through aerodynamic mechanism, which could be to some extent kind of an active control, but the other one is more like a passive, where you try to have this some levers or rods connecting, so that you try to change that effective pitch, which is going to change. Turbines which seek to optimize the blade pitch angle known as zero mills, although some authors refer to the cycloturbine. So these are the now if you see this straight blade wind turbine need to control the power output of the device at high wind speed, and the active pitch control of the blade would result in unnecessary complex mechanism. So this is wind coming in, and this is the rotation or rotor rotation, and there could be blade rotation. So this is where the blade is continuously also changing their pitch. So here it says that this particular work says that the straight blades could be hinged at their midpoint, so that the angle of blades relative to the axis of rotor could be adjusted by mechanical actuator. So here you talk about the mechanical actuators to handle such conditions and all these things. Okay. So the pitch mechanism, which was activated by the movement of aerodynamic forces about the pivot, so that can oppose the centripetal force, and this can act like a stabilizer mechanism or stabilizer mass attached to the radial arm. Okay. So ideally, what it does that the aerodynamic force overcomes the stabilizer moment and permits pitching before stall occurs. That means when they are continuously changing, so what happens is that these blades are continuously changing and rotating like that. So this is how this happening. So in the continuously changing, the flow is coming and hitting the airfoil like that. So there is a possibility of flow detachment. So when that happens, then there could be stall. So by changing the effective angle of attack. So all this whole idea is that your angle of attack of the aerofoil, if this is your aerofoil, so if this is your angle of attack, which is going to expose to the oncoming wind, then there could be a separation and stall. So you effectively change it so that flow remains attack. Once you passes that point, then you again change the angle of attack. Because sometimes, I mean, it's a mechanism because your angle of attack change is required to increase your lift, and the lift here is going to make the shaft to rotate. So obviously if you have more and more rotation, you are going to get more power. That is a simple mechanism. That is what it works upon. But since this is the aerofoil which is rotating and exposed and wind is coming, there could be separation. So you change that, you allow the flow to attach, passes that point, then again you change your angle of attack. So it just continuously, that is what it doing the variable pitch, because it changes its speed. And obviously once you do that, you got significant improvement in the power productions and all these things. So this could be you can visualize little bit, I mean, much better way. Here, if you see, this is how the original, I mean, the whole three blade constructions with the all the connecting rod, you have main shaft and bottom foundation. And if you, so this is the, I would say the front view, and this could be your top view, because you get to see this airfoil, the section of that particular blade, and you see they are connecting with the main shaft, and this is the second link, and how they are from the top view you could see that. And what happens is that this is your, now this is again a top view, this is again your top view, but with variable orientation. Okay, so you could see that the aerofoil here at 0 degree. Now when it came, so this could be the angle, but the second one can, second rod can change it, and again it comes here, so that you make it pretty parallel to the flow, and here again you change it. So effectively you keep on changing and then rotating. So along with the rotation, you keep on doing that. So this is an from the research paper which has been taken. You could see that how they are done. You have a, I mean, this clearly shows you how whole thing is manufactured. So this is your main rod and the and then the arm, and there you have some kind of a spring. Okay, and the spring is connected with another connector, and then the secondary pull rod. So that means if the blade is going like that, you kind of the second rod can pull it down, and that is connected with the spring. Obviously, this should be controlled by aerodynamically. So, well, you say this case how this pitching has been changed, and this case, so the spring plays an active role here. So here is another I mean closer view of this spring system connecting to that, and this is where you could see that how this mechanism basically that secondary rod cam profile mechanism is going to work. So ideally they rotate, and the spring and the secondary connecting mechanism try to change that thing in a kind of an this is a kind of a combination of active and passive control, one could say like that way. Yeah, I mean similar way, I mean you could see this different component of sensors and all these things. Uh, in one foundation, you have multiple of turbines which are constructed, and they are obviously giving you more power output. And like horizontal axis wind turbine, also the blade design is an important aspect of it. So your blade actually commands the performance of vertical axis wind turbine. So various types of blades are shown here. This is lift and drag based vertical axis wind turbine. You have multi-blade vertical axis wind turbine. Then you could see the J-type vertical axis wind turbine here. J-type vertical axis wind turbine here. This is vertical axis wind turbine with kind of a flapper. So all these different kind of mechanism that you could see these designs, these are try to, I mean, improve the performance parameters. So the performance, when you talk about the performance, is essentially you try to maximize your power. That's the final objective. That's what you come up with different kind of sometimes active, sometimes passive mechanism, and try to. But advantage here compared to the horizontal axis, the size of the complete turbine is absolutely way significantly lower, and they can be portable. They could be installed in different places, and then maintenance becomes easier. And you could have a different kind of designs of the blades could be completely carved, twisted, helical, and different shapes and different this kind of mechanical mechanism to control the pitch and things like that. But to be specific, easily controllable system, because the size is way smaller than the horizontal axis wind turbine. Obviously, the power output is also order of magnitude different in horizontal axis wind turbine, but in this case, the size is small. That's why the multiple of them you could put it in one place and try to extract out energy which can cater to small need and things like that. So we'll discuss this part details in the next session. Thank you.